there's another class of antiderivatives that we sort of already know because we know the corresponding derivative formulas. And I want to look at it just by example. So let's calculate this definite integral from 0 to 1 of 1 over 1 minus x squared dx. And if, just looking at this integrand, it seems kind of hopeless. This seems like a complicated integrand to just guess an antiderivative for. But if you think of it in terms of a derivative, right, what we're looking for is some function whose derivative is 1 over square root of 1 minus x squared. If you think back to your experience in Calculus 1 long enough, you might remember that there is a function whose derivative looks like this. And it's inverse sine, right? So since the derivative of inverse sine is 1 over square root of 1 minus x squared, that means the antiderivative of 1 over 1 minus x square root of 1 minus x squared is inverse sine. So the antiderivative we're looking for here is just inverse sine. And of course, since this is a definite integral, we need to evaluate at our bounds and then subtract. So let's do that. We get inverse sine of 1 minus inverse sine of 0. Inverse sine of 1, so remember what we're asking here is, what angle in radians would you put into the sine function to make 1 come out? And that angle is pi over 2. Minus, and then for this second piece, we're asking what angle would you put into the sine function to make 0 come out? And that's the angle 0. And so this whole thing comes out to be pi over 2. All right, so this other class of antiderivatives formulas that we already know that I mentioned is all of the inverse trig functions. So here are all of the derivatives of the inverse trig functions here on the left, right here. Inverse sine, 1 over square root of 1 minus x squared. Inverse cosine, its derivative is actually the same but with a minus in front of it, like that. And then derivative of, all of the rest. For each of these, we get a corresponding integral formula or antiderivative formula, and that's all of these on the right. There are 6 of them, but to be perfectly honest, the only ones that I've ever needed to know are the one for sine, or inverse sine, I should say, and the one for inverse tangent. In fact, I would say that the most important of all 6 of these, surprisingly, is the one for inverse tangent. But it's definitely worth it to know these two, the antiderivative formula for inverse sine and inverse tangent. The others are sort of optional, I guess I would say. In particular, this second one here, the integrand is just the negative of the first one. So another way to write what the antiderivative of minus 1 over the square root of 1 minus x squared is, you could use inverse cosine, but you could also say minus inverse sine of x plus a constant. So, and that's just as good as an antiderivative. These 3 down here, the integrals that produce cotangent, inverse cotangent, inverse secant, and inverse cosecant. To be perfectly honest, I don't know that I've ever used these 3. But the ones for inverse sine and inverse tangent are definitely worth knowing, especially inverse tangent. So let's look at one more example involving these guys. Let's find the indefinite integral of x over 1 plus x to the 4th dx. Now, it seems like this, first of all, this doesn't match any of those inverse trig integrals right off the bat. So you might think, well, what else could we do? You might think, well, let's look at this denominator here. Often, if you have a fraction as your integrand, the denominator makes a good choice for a substitution. So you might use, for u, 1 plus x to the 4th. And in that case, du is 4x cubed dx. And this is actually kind of a problem because, right, to make a substitution work, whatever shows up, right, in this position, it ought to show up in the integral somewhere, but it doesn't. It's not in our integrand. So this substitution actually isn't looking very promising. So let's back up. Right, let's back up. Let's get rid of this, and let's start over. So that was a nice idea for a substitution, but it didn't end up working. So let's see, what else could we do? Well, this denominator here, it looks kind of like 1 plus something squared, right? And that's an okay denominator to have because that, if you integrate, this sort of denominator, sometimes anyway, as we saw on the last slide, produces something involving an inverse tangent. Maybe not inverse tangent exactly, but something like it. So our denominator, the denominator that we have, 1 plus x to the fourth, maybe we should be aiming towards 1 plus something squared in the denominator. But look, we can do some algebra on this. Leave the numerator alone, but we could rewrite the denominator as 1 plus x squared squared. Right? So this actually, right, now that we have it written this way, this set of parentheses gives me a new idea for a substitution. Maybe we should let u be x squared. Then du is 2x dx. And we can move the 2 to the other side. 1/2 du is x dx. And this looks a lot more promising as a substitution because here's x dx. We can turn x dx into du. So let's do that. So now we can do our substitution. We get the integral of 1 over 1 plus x squared squared. Since x squared is u, this gives us 1 plus u squared. And then x dx turns into du. Sorry, 1/2 du. Now we can move that 1/2 outside of the integral since it's a constant multiple. So 1/2 times the integral of 1 over 1 plus u squared du. And now we can use our inverse trig function knowledge, right? This integrand in here is the derivative of inverse tangent, and so the antiderivative of the derivative of inverse tangent is inverse tangent of u, of course, plus a constant as always. Now we did a u substitution, and this is an indefinite integral, so we need to undo our substitution to get back to the original variable, and we get 1/2 inverse tangent of x squared plus a constant. All right, so you can see it's really not, it's not just enough to have these integral formulas in a table somewhere so that you can look them up if you happen to forget them. You kind of have to have them in mind all of the time, because what made it possible for us to do this integral is we sort of had the 1 over 1 plus x squared in the back of our minds somewhere, so that we noticed that we could get there using a substitution. So it really is worth it to keep at least these two integral formulas in mind, because it gives you one more target to aim for when you're doing substitutions or other manipulations of the integrand before you actually write down an antiderivative.